Hello class, Mr. Bean here for AP Physics. This will be part one, electrical circuits, YouTube lecture 8.7.1. And here's the sheet here. And there's some pictures of some circuits here and little outline schematic showing how DC circuits are applied or what are the other concepts associated with it. Down here is this DC Circuits Virtual Lab link. You'll want to click on that. This will come up here, and it's an HTML format. We'll want to go ahead and click on it here, and this will come up. And we'll want to select Lab here. Okay, select this one here, and we'll have this window open up here. And down here we have two options. Do we want a battery or do we want the schematics? We'll want the schematics here like so. All right, back over here. Let's go ahead and scroll down some more. This is part one, electrical circuits. I'll let you go ahead and do the reading here. I don't want to read too much here. And on here, it talks about conventional current flow. Okay, do the reading here. Here's some more stuff on some symbols. And we'll start off by talking about a battery. Okay, so over here is a battery. We're usually used to seeing like a 9-volt battery, AAA, or what have you over here. But we'll do the schematic mode. When we do the schematic mode, is usually a long line here and a short line. The long line here is for the battery. Is for positive, and the short line here is indicate negative. Right. Pause the video at any time to do the reading, and we'll go ahead and continue here momentarily. And let me pause. Okay. All right. So now that we have this circuit here, or now that we're back on, let's construct this circuit here. A simple circuit. So we'll need a battery, which we'll select here, and I want to have the positive end up. We want to kind of match like this here. Maybe we'll select a wire here to make it a little bit bigger. So kind of show a wire here. Okay. Then this is what's called a switch. So we'll want to add a switch here. So I'll go ahead and put on switch here and add it to here like so. And maybe we'll go ahead and add another wire here just to make it, so it's easier to see like this here. Will come straight down like so. Now this here is a light bulb. So we'll need a light bulb, which is right here. And I'm gonna go ahead and turn it around like this, the light bulb. And we will kind of put it like right here. Okay, and let's kind of maybe put it here, maybe up a little bit. Okay, like so. And maybe I'll go ahead and do this here. Hold on, Emma, I'm making a video. Time out.
Okay.
Oh, no, it's okay. Hold on, let me pause. All right, and let me go ahead and add another wire here, like so. And here we go. So we have a switch here. So when I close the switch, we have a current flow. Now, if I switch it to battery, you see the light bulb lights up, but we want schematic form. Now, up here, this is called, so conventional flow is right here. I'll let you read about conventional flow. So conventional flow is what we thank Ben Franklin for this. A positive, we have what's called like positive charges going from positive terminal all the way through to negative terminal. But in reality, the electrons is what's actually moving here. So electrons are leaving the negative terminal here, going this way and going like this counterclockwise to the positive terminal. So that's the actual electron flow, but we're actually interested in what's called conventional flow. Okay, and let me pause. All right, so this next section here is energy and power. There's some equations here. You can pause the video and go ahead and read the reading here, and we'll look at some questions here. First question here is 12.16. It says here a 110 volt toaster oven draws a current of 6 amps on its highest setting as it converts electrical energy into thermal energy? What is the toaster's maximum power rating? Now the answer should be 660 watts. I'll pause here and let you work on it. Okay, to solve for 12.16, let me go up here. Okay, so for here, we should have had that power. Okay, here's the equation for power. P is equal to IV, which is current times voltage. You use this here, and you should get 660 watts. So we'll let you think about that here, and this should get us 660 watts. Next question here. An electric iron operating at 120 volts draws 10 amps of current. How much heat energy is delivered by the iron in 30 seconds? All right, we'll let you think about that problem. I will hit pause. Okay, so to solve this one here, let me go ahead and go drawing here. So we'll start with a formula here that we know that power is equal to, here I have work divided by time, right here. That's the general formula that we used from previous chapters of what power is. It's work done over the amount of time. Let me go ahead and draw a little arrow here. So we want to manipulate this and go ahead and have work here is equal to power times time, like so. And now using the new formula for power in terms of electrical current and voltage, it'll be IV here, IV times T. So now we have what we need in order to solve the problem, and we should get something about, we'll say about around, we'll say 3.6, I'm going to say here E to the 4 joules. Okay, go ahead and hit pause here. All right, now we're on 12.18 question. 1 watt is equivalent to 1. Okay, we should be able to know what this one here is. A watt, we should, what is it in terms of SI units? So watt, we should know is it joules, right, per second is watt. Okay, we should understand that. 12.19, a potential drop of 50 volts is measured across a 250 ohm resistor. What is the power developed in the resistor? Take a look at this one here. And so we want to maybe consider this, look at all the different ways to express power. Okay. Power is equal to, was it IV? That's one way to think about power. And also using Ohm's law, remember Ohm's law was V is equal to IR. Okay, doing some heroic algebra and some manipulation here. I know that power can equal V squared over R. Okay. And I'm going to go ahead and pause here and let you work on this problem here a little bit. So should have got 10 watts for this answer here, 10 watts. Okay, we'll scroll down here to 12.20 and go ahead and read that, and I'll pause and let you work on that problem. Right. 12.20 here. What is the minimum information needed to determine the power dissipated in a resistor of unknown value? The key question here is minimum. What is the minimum? Okay, so take a look here. We see here that so power. So let's start with the basic power equation. Power is equal to I times V. Okay. We have that formulation there. And we look closely here, we have current and we have voltage. So this says potential difference across the resistor only. No, we need more information than that. Current through the resistor only. No, that's still insufficient information. Current and potential difference only. Okay, that kind of looks like this right here. And finally, let's take a look at D. Current, potential difference. So current is I, right? Potential difference is V, and time is here. Yeah, this will work. I mean, that talks about power, but this is probably too much information here. So it looks like C is what we want here. All right, so this will conclude part 1 lecture.